So we're going to kind of look at something new called hybridization. And hybridization is where certain electrons shift orbitals so that bonding occurs. Not every atom does this, all right? So I'm gonna do some that don't shift, some that do shift. What I'm gonna pick though is I'm gonna pick basically the main representative elements. So this is like group 1 and group 2, and then I'm gonna skip the transition metals and then start off with 13 through 18. And we'll see which ones shift, which ones don't shift, and do this hybridization thing. All right, so first off, group 1, we're gonna start off with, let's do lithium, and we're gonna do the electron configuration for it. We're gonna do the shortcut. So lithium's, the shortcut's not much for lithium, but all right, so we have He. And then what's the rest of its electron configuration? Where are we at? 2s1? All right, 2s1. And then the orbital diagram is 2s and then up, okay? So this one doesn't hybridize because this electron's by itself already, so it wouldn't benefit by kind of changing things up. Where does this electron show up if we were doing the Lewis structure? You would just put the dot on any side you'd like, and we just kind of pretend that there's an invisible box around the elements. And for some of the things, we just put them on one side of the box. Sometimes we have to modify the box based on this. Okay, so that's lithium. There's no shifting. Let's move on to the next element. We'll do beryllium for this one because we know beryllium's a little special. Its shortcut is going to be He, 2s2, and then the orbital diagram is going to be 2s up down. Okay. Now check this out. These two electrons are paired up, so they're kind of like in a good state as far as energy goes. We wouldn't expect them to bond because they're paired up. So what happens is this thing called hybridization, where they shift so bonding can occur. All right, so if we do this again, this is going to be the new orbital diagram, all right? And other orbitals that have about the same amount of energy are the 2p's. They have about the same amount of energy. There's nothing in them, but again, same amount sort of energy. You're close enough, all right? So these two electrons are going to split up and go in different spots. So one's going to go here, and then one's going to kind of move over there. Now, an interesting thing about this is it actually hybridizes, which means it combines these two. It doesn't just go over there. They actually shift and change a little bit. So what happens is you get this new hybridized orbital that's going to be a maximum of 4, because you have 1 from s, 3 from p's, and it's going to be called an sp hybridized orbital. All right, it's a combo of the two. And with this one, we're only using 1s. We can only ever use 1s because there's only one orbital for s, but we're also only using one of the p's, okay? So we're using an s and then 1p. So this we would call it just to be sp hybridized, all right? So this would be sp hybridized. So we would just say it's sp, all right? And with that being said, the two electrons now are not next to each other. They're going to be in their own orbitals, and that's why beryllium can actually exist like this, where it's 180 degrees. If it didn't do this, it would look something like that, and you wouldn't get bonding, all right? You would just get it, you know, these electrons together doing their own thing. And I guess technically they could bond in different ways, but we're not talking about that right here, okay? So here's the original electron configuration and orbital diagram like we did last chapter. Here's what happens. It spreads out any doubled up ones, if it can, spread them out, and then it forms this hybridized kind of version of it, which is now condensed into something called an sp orbital, all right? Cool? Okay, let's do the next one. All right, so next up we have, after beryllium, boron. All right, boron is He, 2s2, 2p1, right? And then He, 2s up down, 1, 2, 3, 2p up. Okay. What do you think happens with this one? One, does hybridization occur? And the answer is yes. There's one that's paired up and there's some empty spots for it, right? Okay, so it does happen. What is it going to look like? All right, one of those S's is going to jump over to the P's, right? And that's going to cause some shifting. So we're going to end up with this, right? S, and now there's two P's, right? So this one we would call sp2. sp2. Meaning that there's one of the electrons in the S and then there's two in the P's. All right? And because now there's three spread out, we look at this and say, all right, how can we get three electrons here as far away from each other as possible? And we would get that kind of triangle looking thing. And we know that this will now form trigonal planar, right? AXE, all that kind of stuff. So this is the reason that it ends up looking like this instead of something like that, where it was originally like that. So these are not what's going to form. This is what's going to form. Does that make sense? Okay. And then the next one, carbon. All right, carbon is He. 2s2, 2p2. All right, orbital diagram. Up, down, up, up. Okay, you ask yourself, would this benefit by moving an electron over from the S to the P? Would you be able to bond more things to it? You look at it and you say, oh, there's an empty spot there. Awesome, it works. All right, so then we're going to do that. So we'll have 1, 2, 3, 4. This is our S, P, P, P. And we moved one arrow from the S over to the P. So now this one would be S, P, 3. All right. And because we have 4 electrons by themselves or unpaired, you would get 4 dots around this. 1, 2, 3, 4, instead of originally them being paired up, all right? And that would allow us to have the tetrahedral shape, all right? So SP, SP2, SP3, all right? Now, this happens with these atoms. It can also happen with double bonding and whatnot, which we'll get into a little bit later. But this is kind of like the beginning of it. Do you guys have any questions with these 4? No? Okay. So these 4 are interesting. Let's look at the next 4. So after carbon, we go to nitrogen. And let's see if it works here. All right, so we have 2s2, 2p3. And then down, up, up, up. All right, so we end up with this here. Would this benefit by kind of moving over? Bonding? No, it won't, right? So for this one, we'll just kind of leave this the way it is. And it would do what we would expect it to do. There's going to be 2 that are paired up. We'll call those our S's. And then the P's are by themselves, so we'll kind of move them around like that. All right? So then it doesn't happen. And as you can imagine, the same for the other ones. They're not going to shift either. So the next one we have is oxygen, He, 2s2, 2p4. And then we have He, 2s up, down, and then 1, 2, 3, 2p4. Up, 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 and then, that down's not good, down. So we have 2 paired up, single, single, which is what you expect when we're looking at oxygen, right? We kind of go around and then we say we double up. Well, those are like the S's, those you can think of as the P's, and these 2 would be the 2 that are by themselves that are involved with bonding, all right? All right, and then after oxygen, we have fluorine. All right. 2s up down, 1, 2, 3, 2p, 1, 2, 3, 4, 5. There's only one by itself there, no shifting. Just start filling it up, and you can have your single on any side you'd like, anywhere. All right, and then for the last one, neon, they're all filled up, so it's not going to do anything either. So neon, we have HE, 2s2, 2p6, HE, 2s, 2p, and then up, 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 down, down, down. So it's completely filled. There's 8. You just put them all around. There you go. Okay, any questions with that? Same thing's true in the groups. So all of the group, like underneath nitrogen, we have phosphorus. So it would be the same, right? Except the numbers would change, but it would be the same kind of like dots and everything. Oxygen underneath that. You have sulfur, same thing. Under fluorine, you have chlorine. All these would be the same. Now that's true with these as well. So this whole group will do this shift. This whole group will do the shift. This whole group will do the shift. So for this, there's only 3 that you have to kind of remember that do this kind of hybridization shifting, all right? It starts with beryllium, ends with carbon, and it's sp, sp2, sp3.